Good evening.
Good evening. How you doing?
Good. How are you?
Not too bad. Just checking out my stuff here.
Yeah. Ready for the weekend?
Yes, definitely. I need it more than ever.
Do you have any classes on Fridays?
I don't. That's where I use my time, and well, usually I use my time to try to grade lab reports and stuff like that. So
Hmm.
hopefully I'll finally get everything caught up, and that'd be nice.
That'll be cool. Yeah.
Um, how about you? You got anything going on this weekend?
I'm gonna study for our test.
That'd
I'll
be appropriate.
play catch up on the homeworks and all that stuff. So
Yeah, that's kind of there's actually some fun to it. It's just yeah, sucks that you have to, but I get you.
yeah, we I have Monday off of work, so that's a little bit helpful
Oh yeah,
too.
that's cool. Yeah, we love days off.
Yeah, they get all the better.
We don't get any more until November 5th for election day or whatever, and that's about it.
Oh, you guys get election day?
Yeah, mainly because our campus is one of the voting sites.
Oh, gotcha. And then like Thanksgiving, I guess, like a Thanksgiving break or whatever.
Yeah, Thanksgiving's the next one, so and I think that's like the 25th or 24th that we get off.
Yeah, I think it's late this year.
Yeah. So I've been working on trying to make what I think is a good but easy test for my online tests, especially since I moved them back. Uh, Not sure I succeeded, but I'm trying.
Mm.
Danielle or Tanika, if you have any questions, feel free to ask. I'm almost finished setting up the grade book. There's a couple different courses I have where the grade book got kind of razzled, frazzled a bit, and I'm trying to fix that. So I hope to have that done maybe even tonight. I just finished a test, which I didn't think I was going to finish till about 10 o'clock tonight. So I'm at least ahead on that. We got about a minute before class starts. You're welcome to ask me any questions you might have. Oh, we got another person. Woo-hoo. Oh, and they got a cool galaxy photo, Milky Way photo. Hmm.
Not really class related or schoolwork related, but did you see the Newport News shipbuilding got there was an article on like a lot of their welds were basically
Oh,
not
yeah, I heard
good.
about that.
Yeah, and they
It's
someone was
like
like
three
forging this.
subs and an aircraft carrier.
Yeah, they're like forging the signatures and stuff.
Oh, that's not good.
No.
Yeah, I
It's
don't
pretty
like being
crazy.
in the sub, period. Can you imagine being in a sub that you have has questionable welds?
Yeah, no way. And that sounds awful.
Yeah, it's not cool. Yeah, I just heard about it. Actually, I was sitting here thinking, I was like, maybe I should start a career in welding. I think I'd really like to do that.
Yeah.
But I know it's
Hey,
hard to tell and probably really, really exhausting.
yeah. But they need welders. I'm sure it's pretty good money.
Yeah, that was the thing. They make quite a bit more money than we do as teachers. So
Yeah.
uh, at least starting off, they did. I don't have the room to go up that we do, but we don't have that room to go up either. So
Yeah.
we had one professor, or quote unquote professor, at my old college, and he was the highest paid faculty member, but he was the only one that was paid even remotely ranked to the rest of the state of North Carolina. And he was, really big because he was making like $78,000 a year. But literally the next highest paid faculty member was only making like 56.
Oh wow, that's a big jump.
Yeah.
That's
And they
crazy.
just increased our contact hours to 21 from we had been doing like 19 or something like that or 18. And they upped that in addition to us finding out about how bad the pay was. That's when I left.
Oh man, that's crazy.
Yeah, it was terrible, but we're getting better. All right. Well, it looks like I've got 60 you folks here. Does anybody have any questions before we get started? Hopefully everybody got my message regarding pushing the test off. also, hopefully everybody is not upset with that. If anybody is, I might even be able to swing a test for you to take as early as tomorrow if you want. You just have to let me know tonight. So if that's really been a problem by me pushing it back, I understand. I know how exhausting that can be when you know, put all this time into studying and then something gets set back. But usually after I took a little while, I usually felt a little better about having a couple more days. And since I didn't give you, since I didn't announce it the day of the test, that helps a little bit. I know it really is a bothersome thing when you stay up all night, you know, 2 or 3 in the morning, and then you go to bed and you get up the next morning and go in, and then they say, "Oh, we've decided to push the test off." That's just aggravating. So hopefully I got it early. So no questions. All right. Well, the last time we did something that was probably scary. If it is scary, don't feel bad. That's perfectly normal. Okay. If you try to look at it like what you might have to do in a calculus class, maybe that makes it a little less scary, but it is a big, robust integral problem. So I'm going to show you some more integral problems today, and then we're going to hopefully have enough time to give you some results regarding electric dipoles, and maybe even start into the next chapter, which is Gauss's law. So let's go ahead and get started. I'm going to share my screen with you folks. And it should be coming up any second now. And before we get started, I want to remind you of our fancy little formula that worked out for us. And that is a small segment, a differential element of an electric field, dE, is actually equal to dq over 4 pi epsilon naught. Then if we want a vector, we need to multiply it by a vector. Ideally, you could multiply it by a unit vector, and then you wouldn't screw up the magnitude and all that stuff. So that's sort of what I'm actually doing. I just avoided that because there's not a lot of people necessarily that know how to make unit vectors. But the vector that I'm going to do is rp minus r dq. If I really wanted to make that a unit vector, what I would do is take that vector and divide it by its magnitude, and that would make it a unit vector. But you might notice that's the exact same thing as if I wrote the magnitude of that vector down here. Remember, that magnitude is the separation between the differential charge element dq and the point at which we wish to know the electric field. So if I put that magnitude down here, then you would expect it to be squared because that's, you know, Coulomb's law is a 1 over r squared law. But in order to make that top a unit vector, we have to add another. So that's another way of looking at it beyond what I told you last time. Both ways work, of course, but that's the actual formula. Now, what I want to do is use this to solve yet another somewhat difficult problem. So what I'm going to do is I'm going to imagine a loop of charge. So like a hula hoop, if you will, of charge. So let me draw a coordinate system. I'm again doing the coordinate system specifically so we can all be on the same page and use very specific symbols and stuff like that of exactly what the problem is. So I'm going to, I don't think I want to put it there. I think I want to put it a little further over here. Okay. I also want the axis to be like that. Whoa, Nelly. Did not mean to do that. Okay. I also I wanted that to be up there going through the middle. I'm going to do, okay. So this axis right here is the x-axis coming out of the page. This is the y-axis that lies directly in the page, and the z-axis also lies directly in the page. So the x-axis comes out in the front, the negative x-axis goes out in the back. I'm going to draw a current, or excuse me, a charged loop of wire. Whoa, Nelly. And again, I still don't know why my program does that and becomes an eraser all of a sudden. If anybody knows how I can set that, stop doing it, that'd be really great. So this is supposed to be a circular loop of charge. So far, I hate it, so that's nice. And I really got to start taking medicine or something because my OCD is not making life any easier here. Oh, that's still bad. Let's see if I can do it with the auto thing. Yes, that works pretty good. Now I'm going to try to move that a little bit. Yeah, that looks still a bit crooked, but anyways. So that's going to be our charged hoop of wire, if you will. And what we're going to imagine is that the charge is Q. So that's our total charge. And we're going to say it's uniformly distributed. I'm not finishing any words today. I'm just going to put dots at the end of all of them. So we have the total char and we have uniformly dist, so on and so forth. Now, what I'm going to do is I'm going to say that this particular ring has a radius big R and is really kind of infinitesimally thin. I don't have to worry about the thickness. I drew the thickness on there so you could recognize it as a thing, but it's not significantly thick. It does have a radius R that we assume we know, and it has a total charge, capital Q, that we assume we know. I really don't like that either, and because I didn't take my medicine, I'm going to address it. So Q equals the total charge on the ring. Okay. And uniformly distributed is basically going to tell me that lambda equals a constant, which in this case will be Q over 2 pi R. Okay. And it's lambda because this is like a one-dimensional object, not unlike the straight wire we did last time. But in this case, it's just not straight. So if we actually took the total charge and divided by the total length of the loop, which is the circumference formula, then we get the actual constant. So what I would like to know specifically is what is the electric field at a point Z directly above the symmetry axis of the circular loop. Okay, so that Z is something we know, the capital Q is something we know, and the capital R is something we know. Lambda is not something we know, but we can immediately get it because I just told you it's Q over 2 pi R. Okay, so what I'm going to do is I'm going to imagine an actual charge, a dq somewhere. The best way I think to do that would be maybe come over here like this and let this angle right here be an angle theta. And then I'm going to allow that one line to wiggle a little bit beyond, and then this angle right here is going to be d theta. So that's the itty bitty angle in there. And what that tells us is that this little bit right here, that's going to be our dq, and its length is r d theta, which I'm going to call dl. Okay. And this little guy right here, I'm saying is dq, which equals lambda dl. So again, it meets our criteria, which remember I told you dq would be either lambda dl or sigma dA or rho dV. So it's one of those. Now it's a little complicated, but remember the formula is basically that we have to go through this formula here and pick each symbol and then make sure we actually fill out and figure out exactly what those symbols are. So here's our solution. So I've got this formula right here. I need a vector RP that points from the origin to the point P in question. Does anybody know what that vector is? You can use your I hats, J hats, and K hats, or your X hats, Y hats, and Z hats if you like. Maybe if I drew it, that'd make it a little easier for you guys. So it has to go from the origin to the point at which we wish to know the electric field. The point at which we wish to know the electric field is this little point, parenthesis 0, comma 0, comma Z. So that vector is RP, and hopefully y'all figured it out by now. But
0, or is that K hat then?
yes, ZK hat, that's it. Okay. Now, the other one is pretty straightforward, but it seems a little confusing. I'll just remind you that your calculus teachers and your physics book, when it talks about calculus stuff, will often say that something goes from R to R plus dr, or from X to X plus dx, that kind of thing. So what I'm going to do is I'm going to imagine another vector. This time I'm going to make it blue, and this one's going to be a vector from the origin to DQ. So I need a vector from the origin to that little DQ I drew, and we're going to consider the DQ to be at R theta, basically. So this is the vector R DQ. Anybody want to? Oh, well, I'm not going to do that. That's kind of harsh. But what we need to realize is that we have a positive Y component right here and a positive X component right here. So there's the Y component is the one going from left to right, and the X component is the one that appears to be coming out of the screen. Those are the X and Y components. So now hopefully it makes some sense when I write R sub DQ is equal to, notice the length of the R vector, the R DQ vector is R. And if you take R and multiply it by cosine theta, you'll get the X component. So I'm going to say R cosine theta I hat. And if you multiply R times the sine of theta, you'll get the Y component. So I'm going to say plus R sine theta J hat. So that really is what our RDQ vector and our RP vector is. So this, I wish I would have wrote that in blue. That would have made it a little more color coordinated. I'm actually going to do that just to make it clear for you guys to understand, because I drew the RP vector in purple and I drew the RDQ vector in blue. So I think it might be nice to go ahead and just write RDQ as R cosine theta I hat plus R sine theta J hat, like that. And that's just a little better looking, and you can sort of see that I'm trying to correlate it without getting the figure so busy with all the symbols on it. Now, we also need the vector that we have referred to as RP minus RDQ. Now remember, RP minus RDQ means you got to turn RDQ backwards. So RDQ, or excuse me, RP minus RDQ. Yes, you got to turn our DQ backwards. So this blue one will now be pointing towards the origin with its tail out there against it. And then the blue vector and the purple vector are head to tail. And the way you add two vectors head to tail, which is adding now because RP minus RDQ is the same thing as R plus the negative of RDQ. So the actual vector is going to go from the DQ to the point P. So that's our RP minus RDQ vector. So I'll keep that color too and just say RP minus RDQ. Since I've drawn it that color and I'm now writing the definition of it in that color, hopefully that helps you see exactly what we're talking about. So this is going to be ZK k hat minus r cosine theta I hat minus r sine theta j hat. So that's what our RP minus RDQ is. And then the last thing we need, I'm going to go back to purple because that seems to be what I'm doing the solution in. So the magnitude of RP minus RDQ is what we need now. I think you can see that that would be z squared plus negative r cosine theta squared plus negative r sine theta squared, square root of all that. Clearly, the last two terms have a common factor of r squared. So I can factor that out, and then I have z squared plus r squared parenthesis cosine squared plus sine squared, which is just 1. So ultimately, this gives us just the square root of z squared plus r squared. Now that might seem scary because we've got a z and an r and all this stuff, but remember z is a given, r is a given, so we're not necessarily going to have to do too much terrible work to do this. So now we're in a position where we can go ahead and write what E, the electric field, is. So E, the electric field, is in fact the integral of dE, which is in fact taking my constants, because the dq is going to be lambda dl. Everybody sees that right here. And the dl is going to be r d theta. So basically, we're going to get the little r there and the little lambda there. They're both going to be constant. So I'm going to pull them outside of the integral and write lambda r over 4 pi epsilon naught. And then I have to take the integral. Notice now all we have is just d theta on the top, but we still have the z k hat minus r cosine theta. Well, actually, let's not even try to write it in there. That'll get too nasty. I'll just say, whoa, Nelly, there it goes again, erasing stuff. So I'm going to say d theta, and then I'm going to say dot, 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 because we know that's RP minus RDQ. And then all of that will be over z squared plus r squared to the 3/2 power, because it was a square root, but we had to cube it according to the formula. So that becomes a 3/2 power. Now, the neat thing is, because we're integrating with respect to d theta, and you see that basically z is not a function of theta, and theta doesn't appear anywhere else in the denominator. So we can actually pull that denominator out in front as well. And now we're going to get E is equal to lambda r over 4 pi epsilon naught z squared plus r squared to the 3/2. All that is going to be multiplied by the integral of, now I'm going to start writing the individual terms. It's going to be, whoa, there it goes again. It's going to be d theta times zk hat minus r cosine theta I hat minus r sine theta j hat. And then close parentheses, and I'm going to integrate this from theta equals 0 to 2 pi. Now, I want you to notice that in principle, this dE vector is right there. That's our dE vector, okay? Now, notice that dE vector, when I'm talking about a differential area element where I have one located, everything's fine. But if I go to the diametrically opposed spot, say right here, then that's going to create another dE vector that points up like this. I think you can see that those two dE vectors actually cancel each other's x and y components out. So the x component of the purple dE vector is the negative of the x component of the blue dE vector. And the y component of the dE vector is the negative of the y component of the blue dE vector. So both the x and y components will cancel out, but the z components add to each other. So that tells us right now we should expect when we integrate this to get 0 for the I hat term and 0 for the j hat term. Okay, so that's one way of thinking about it. Another way is you realize you're going to integrate cosine from 0 to 2 pi, and clearly cosine is half of a lobe from 0 to 90, and then it's a whole lobe from 90 to 180 to 270, and that's a whole negative lobe. And then it's a positive lobe from 270 to 360, and that's again a half a lobe. So the two positive half lobes are exactly the same area as the negative whole lobe. So the actual integral of cosine theta between 0 and 2 pi is clearly 0. So mathematically, that's why the I component disappears. If you look at sine theta, it's an entire lobe from 0 to 180, and that's a positive lobe. And then from 180 to 360, that's a whole lobe again, and that lobe is negative. Those two lobes, of course, are completely equal, are completely the same shape, except one's positive, one's negative. So again, integrating from 0 to 2 pi, the sine of theta becomes 0 as well. So there's two reasons, one physically and one mathematically, for why the I and j components are going to go to 0. That being said, I'm still going to work it out like we don't know that. Okay. So now I'm going to say, oops, go back to my purple. And now we're going to say lambda times r over 4 pi epsilon naught z squared plus r squared to the 3 halves times, I'm going to say the integral of z, and actually let me put this a little better. I'm going to do a little better than that. I'm going to say z k hat integral d theta from 0 to 2 pi. And then I'm going to say minus r integral cosine theta d theta. That one's times I hat, and this is theta equals 0 to 2 pi. And then I'm going to say minus r j hat integral sine theta d theta, and this is theta equals 0 to 2 pi, and that's what we got to integrate. So again, I'm going to write lambda r over 4 pi epsilon naught. I generally like to write the distance away as the last thing, so I'm going to write it as r squared plus z squared to the 3 halves. That's just a matter of preference. It doesn't really matter too much. We can clearly see, whoa, Nelly, there it goes again. We can clearly see that the integral of d theta from 0 to 2 pi is just going to be 2 pi. So I'm going to write this as 2 pi z k hat minus r I hat. Now, the derivative of sine is cosine. Therefore, the integral of cosine is sine. So this is going to be times the sine of theta, and I'm going to evaluate that from 0 to 2 pi, which means the sine of 2 pi minus the sine of 0, which the sine of 2 pi is 0 and the sine of 0 is 0. So this is just going to be 0 minus 0. Ah, darn it, there it goes again. And then similarly, I'm going to say minus r j hat. The derivative of cosine is negative sine. So we could actually say the integral of sine is, or actually we just say it that way. The derivative of cosine is negative sine. So the integral of sine of negative sine is positive cosine. So I could make this into a positive, and now I'm going to say here is cosine theta, and I'm going to evaluate that from 0 to 2 pi. So that's going to be cosine 2 pi minus cosine 0. The cosine of 2 pi, of course, is 1, and the cosine of 0 is also 1, so we're going to get 0 for that as well. So as advertised, the I hat and j hat terms disappear. And now we can rewrite this E in a new way. I'm going to say E is equal to, I'm taking the 2 pi that we had right here. I'm taking that and I'm putting it by the R for a very good reason. And then I'm putting the lambda in front of that for another very good reason. And then after that, I'm going to put the Z, and I'll save the K hat for later. But all of that's going to be over 4 pi epsilon naught R squared plus Z squared to the 3/2 power. And all of this will just be in the K hat direction. Now, does anybody see why I wrote the lambda and the 2 pi R that way? What is lambda times 2 pi R? So we found, as I wrote up here, that Q over 2 pi R is lambda. So if I multiply lambda times 2 pi R, I should get Q. And that's what we just did. So I'm going to say this is QZ over 4 pi epsilon naught R squared plus Z squared to the 3/2 power in the K hat direction. And this is the final answer. Anybody have any questions on that one? All right. So that's another use of Coulomb's law in integral slash vector form. So we actually had to create a vector form of the equation. We had to create an integral form as well by treating the Q as a differential Q. And then, of course, stating that dq should be something like lambda dl, sigma dA, or rho dV. Remember also, I told you that the units of those quantities should be like lambda would be coulombs per meter, sigma would be coulombs per square meter, and rho would be coulombs per cubic meter. So hopefully that helps everyone with that particular problem. I don't like how not good this green vector shows up, so I'm adding a little bit of accent to it because, again, I am OCD. So we're going to leave that there. Oh, God, there it goes. Anybody have any questions about that? There it goes again. All right, that's making me so mad. Anybody have any questions about this before I move on to the next one? All right, so the next one's going to be sort of similar. So what I'm going to start off with is I'm going to draw a loop again. So this time it's going to be a disc though, instead of a loop of wire. So I'm going to draw a circular disc, something like that. That doesn't look too terribly bad. I'm going to draw a coordinate system like this. And I'm going to say that this is my x-axis, this is my y-axis, and this is my z-axis. I'm also going to say that this disk has a radius of big R, which we know, and has a total charge Q. And here I go again, not fitting things in, okay? But it is uniformly distributed. Again, and again, I would like to know the the electric field at on the z-axis a distance z away above the center of the sphere of the circle. Notice this circle is actually not centered up that well. I'm kind of not happy about that, but we're going to go with it and pretend like it is. Okay. Now, this one is not one that lends itself easily to our neat little formula, but we did discover something. What we found out was that a loop of wire has an electric field given by Q times Z over 4 pi epsilon naught R squared plus Z squared to the 3/2 power, all pointing in the upward direction. And you probably remember that when you were trying to, for instance, find the area of a circle, you used little washers. So that little loop of wire looks like a washer, and that's the way I'm going to use it. So what I'm going to do here is I'm going to imagine a loop like this, whose radius is just plain R, and whose thickness is dr. So I'm going up here, and I'm saying that this distance is just dr. Now, if I took and cut right along this little line, notice I put a spot right there. If I cut right along that line, what I would find is that this particular ring that I drew would actually be shaped like this. Okay. And that is almost a rectangle. If it wasn't for that little bit of triangle on each end, it would be a rectangle. We know it's not a rectangle because the inside edge has a length given by 2 pi times r, and the outside has a length given by 2 pi times r plus dr. So you can see that's 2 pi r plus 2 pi dr. So you might realize that the extra little bit here is pi dr, and this little bit right here is pi dr as well. So in principle, the actual area of that, which I'll call dA, is actually equal to 2 pi r times dr, because remember this thickness is dr. So that's just the thickness, or that's just the area of this rectangle right here. Okay. If we want to actually do the whole area, though, we have to include the two little triangles, and the area for a triangle is 1/2 base times height. Well, the base is pi dr, and the height is dr. And then we've got the other one that's the same thing, pi dr times dr. So you see, you could call this 2 pi r dr plus terms of order dr squared. So they write that O with a little Charlie Brown haircut, if you will, to mean terms of a certain order of magnitude. So what we see here is the difference between the real area and the area that I'm getting ready to use, which is 2 pi r dr, is really just 1/2 pi dr dr. And the integration process requires us to do a Riemann sum, and that means we're going to take a limit as the width of the little dr gets smaller and smaller and smaller. We're going to take the limit, in other words, as dr approaches 0. So if dr is approaching 0, dr squared is nothing compared to dr. So the fact that we're multiplying a macroscopic quantity like 2 pi r times a microscopic quantity like dr means it's going to be big compared to dr squared, and so big that we can just ignore it. Okay, so that's physically the reason why we're allowed to do what I'm getting ready to do. So I am going to say specifically that this is dq. Well, let me make it lowercase dq. Well, I'll make it dq like that. That's going to be 2 pi r dr is what that is. And we already found that the differential electric field is going to be dq times z over 4 pi epsilon naught times r squared. Oops. Now we're doing a little differently because it's not big R anymore. It's the little r squared plus z squared to the 3 halves. And all of that's pointing in the k hat direction. So if you'll notice, that's exactly the formula that I came up before. QZ over 4 pi epsilon naught r squared plus z squared 3 halves. You see, I'm just using that because I'm treating that ring of charge that I just solved with the more brutal integration techniques. I'm treating that as a differential charge. And I already know what the differential electric field due to it is. It's dq times z over 4 pi epsilon naught, blah, blah, blah. Right? Now all I have to do is replace I'm actually missing something on there. Now all I have to do is replace the dq not with just 2 pi rdr, but with 2 pi rdr times, dang it, there it goes again. But with 2 pi rdr times sigma. So just to make sure you guys remember, I'm going to zoom in a little bit so we can look at it. And I'm going to say this is the charge per unit area, sigma, that we learned about, times 2 pi r dr. So that's what our differential charge element is. Good Lord, that's small. I should probably write it a little bigger. Anybody have any questions about that? All right, so now I can say E is equal to the integral of dE, which is going to be, this time I can pull the z and the k hat out in front as well as the 4 pi epsilon naught. So I'm going to say z over 4 pi epsilon naught times k hat is what goes here. I don't like how that turned out. And now I have the integral of, instead of dq, I'm going to put sigma times 2 pi r dr. I've already gotten rid of the z out in front. And down in the bottom, I'm going to put, just because I'm getting ready to integrate with respect to r, I like the r that I'm integrating with respect to be last. So I'm going to write this as z squared plus r squared. Yeah, exactly the opposite from what I liked previously. So that's what we got there. Now, remember, just to keep your wit about you, could anybody tell me what sigma would be? We know the radius of this disk is r. We know the total charge is q. Can anybody guess what sigma would be if we had to calculate that?
Would we use the Pythagorean theorem?
You don't have to, not with this, because we're just talking about the little sigma, this little quantity right here. And remember how we define that? That's the charge per unit area. And then, of course, you multiply that by area. What we said was the area is 2 pi rdr. So can you guess what sigma would be?
2 pi r dr?
Almost. Remember, the units are coulombs per square meter. And it's supposed to be a charge Q uniformly distributed over the disk. I don't mind I'm not wasting this time. I don't mind using this time because it's really important that you guys understand how the dq works with the lambda, the sigma, and the rho. So I really want y'all to get that. Anybody else want to offer a idea? I'm going to open up my chat too, in case somebody's typing something. They sometimes do that. There it is. Nope, no, no guesses. Okay, remember it's the surface charge. It's the surface area charge, if you will. So it's the charge per unit area. The area of the entire disk is pi r squared. So sigma, whoa, might help if I use a pen instead of a laser pointer. Sigma is equal to Q over pi big R squared, because big R is the radius of the circular disk. Okay. So that's all I wanted to point out, just so you'd have a little bit better feeling of what lambda is and what sigma is. Notice on the previous one, we actually said that lambda was Q, the total charge, divided by 2 pi r, which is the total length of that loop. So that was what I was hoping to let y'all see by showing that, and then just make the analogy when we went to the other one. But that's okay. I mean, it's perfectly fine. That's the purpose of us teaching, is so you'll understand at least next time. So now I can pull out some more stuff. In this case, it's actually pretty easy to integrate it, because you see we actually have an R here and even a 2, and we can do that substitution, the U substitution. So what I'm going to do is I'm going to say let U equal Z squared plus R squared, which implies du is equal to 2R dr. So if I keep this 2 and this R and this dr up there, then that's the equivalent of du. So what I'm going to do is I'm going to write equals. I'm going to put the sigma out in front of the z, and I'm going to put the pi out in front of the z, and then I'm going to write the z, and then 4 pi epsilon naught, and then I'll write the k hat after it. And now I'm going to integrate. Specifically, I now have u to the -3/2 times du. I haven't done anything about my range of integration now, but just to let you know, I would have been integrating it from r equals 0 to big R. That's what it would have been. Okay. But now that I've made this substitution, I get to do something slightly different, and maybe even just use that range of integration. We'll see. So you can see the actual pi does cancel out here. I'm not sure if I'm going to want it later, so that's why I haven't done that. But we do know the integral of u to the -3/2 is u to the -1/2 times -2. It's actually u to the -1/2 divided by -1/2, but when you divide by -1/2, you're doing the same thing as multiplying by -2. So I'm going to go ahead and say this is equal to negative sigma 2 pi z over 4 pi epsilon naught k hat times, now we're going to say z squared plus r squared square root 1 over that, and I'm going to evaluate this from r equals 0 to big R. So that's what we've got to do now. I can go ahead and work that out. Again, I'm still leaving the 2 pi and the 4 pi in the bottom, and we're going to probably see why in a little bit. So this is negative sigma 2 pi z over 4 pi epsilon naught k hat. Now what I'm going to get is, when I evaluate it at capital R, it's going to be 1 over the square root of r squared plus z squared. So you can see I can write the distance 1 second like I normally like to do it, minus, now I've got to do 1 over the absolute value of z, because notice I'm plugging in r equals 0, and then I'm taking the positive square root of z squared. Hence, it's the absolute value of z. Now, I'm almost done, but for instance, you can tell that r squared plus z squared to the square root power in the denominator makes a fraction that's actually smaller than 1 over z. And because of that, this quantity in the parentheses or in the brackets is negative. So I'm going to absorb that negative and reverse the multiplication or reverse the subtraction, and I'm going to multiply through by z. So when I do that, I'm going to get sigma times 2 pi, and that's all going to be over 4 pi epsilon naught, and then times k hat. And then now I'm going to say, when I multiply z by 1 over absolute value of z, I just get 1. And then when I multiply z by 1 over the square root, I get the 1 over the square root times z. So this is going to be r squared plus z squared. I don't like that z that I just did there, that square that I just did there. So that's the actual answer. We can go ahead and cancel that out, or I can go ahead and make use of exactly how this relates to say Q. So for instance, we know that sigma is supposed to be Q over pi r squared. So I can replace that and say big Q over pi big R squared times sigma, or excuse me, times 2 pi, all that divided by 4 pi epsilon naught, all that times k hat times 1 minus z over the square root r squared plus z squared, like that. When we look at it this way, now you can finally see that this pi cancels out with that pi, and we get a slightly different form of the answer. We're going to say now that, in fact, this 2 can cancel out with that, leaving a 2 down here. So now I'm going to say the answer is Q over, over 2 pi epsilon naught big R squared, all of that times k hat times 1 minus 1, or excuse me, 1 minus z over the square root r squared plus z squared, like that. So that's sort of the answer that we're shooting for. Anybody have any questions on that? All right, let's go ahead and write it nice and neatly and box it off. So this is going to be E is equal to Q over 2 pi epsilon naught r squared k hat times 1 minus z over the square root r squared plus z squared. Now, if you try to examine this for really small z, in other words, for z that's very small compared to r, then that's sort of the limit as this circular disk becomes infinitely large. Remember, in the physics world, a factor of 100 is really good. A factor of 10 is probably just on the edge of being good enough, or is good enough. So if we had z being 1 centimeter, and then r was a whole meter, then that would be a factor of 10 bigger. So probably it'd look a lot mathematically as if it were infinitely large. In other words, if I did a calculation for the electric field 1 centimeter away from a disk that's 1 meter in radius, I would probably get an answer that looks very much like the reality, even though it's 1 meter by 1 centimeter. Okay, so that's what we're looking at here. But if we do imagine that z is much less than r, we could in principle go through and use a binomial expansion and that sort of stuff. But I think what you'd ultimately see, and you can sort of make it out, it's a little harder here, but you can sort of make it out that basically you would get sigma over 2 epsilon naught. It's a little easier to make out when I'm at this point. Let's show you here. At this point right here, or either of these points for that matter, if we look right here, this 2 pi cancels out with this 4 pi, leaving just a 2. So we get sigma over 2 epsilon naught in the case where Z is much, much smaller than R. So if this is much, much smaller than R, then this term being added to R squared is just going to give me R in the bottom. And then Z over R is approximately equal to 0 because Z is way, way less than R. So when you cover up this whole last term right here, you see that you do get sigma over epsilon over 2 epsilon naught. So that turns out to be a fact. So I'll say, therefore, for Z much, much less than R, I just can't leave good enough alone. So anyways, Z much less than R gives you E is equal to sigma over 2 epsilon naught K hat. And what that means is on top of the plate, above the plate, it's going to be pointing upward, and then below the plate, it'll be pointing downward. Okay, and meaning if you got a positive charge on the plate, that is. If it was a negative charge, it'd be pointing downward. But the main thing is that's it. So these are both very important results. In fact, I will derive this one on its own a little bit later. But that's both of those are very important. So anybody have any questions on that? So that was done an entirely different way than the way we did the other one. But to be honest with you, these 3 integrals I've done for you are essentially just about all the ones you could possibly do. There are some more. And then there's a lot of ways I could tweak these to make them slightly different. All of them you're expected to be able to do, especially on a homework, but even on a test, really. So I want you guys to really just focus on doing these over and over again. Each one of them. Probably start with the very first one I did, then the second one I did, and then the third one I did. But the most important thing is just do the first one and then do it again and then do it again until you can do it on your own without looking back at it. And then maybe you can try the second one. Again, keep trying until you can do it without looking at the solution, and then try the third one. Third one's a little more complicated, but it actually turns out to be a bit easier. So anybody have any questions on that? All right, now that we have that, there's a couple little things that we need to discuss in chapter 21 that I haven't really done. And I normally do the long derivations of these. I'll sort of do a little bit of a derivation. What I'm going to do is I want you guys to imagine a dielectric, or excuse me, an electric dipole. So we did electric dipoles earlier. I also did a 4-part series on my YouTube channel of calculating electric fields and forces due to an electric dipole. Electric dipole is basically anytime you have a negative charge, like negative 1.11 nanocoulombs, separated by some distance from a positive charge that's also 1.11 nanocoulombs. So anytime you have an equal charge but opposite in signs and 2 charges separated by a distance, that makes a dipole. The problem is it doesn't really make a dipole. So if you just had 2 charges floating in space, they've got no reason to stay tethered to one another, so they're not going to. But it turns out that, for instance, the water molecule is what we call a polar molecule. And in fact, what I like to do when I'm thinking about water molecules is I imagine it like it's Mickey Mouse. So there's Mickey Mouse's head, and here's Mickey Mouse's ears, something like that. These really are just the hydrogen, and this is just the oxygen. Okay. Well, if you look, hydrogen is the top left of the periodic table. That means it has, since it's at the top and it's at the far left, it sort of has the least hold on its outer electrons than any other element in the periodic table. And then if you look down a row and go 2 from the far right end, you'll see oxygen. It's 2 spaces from the far right end. And those 2 spaces means that the oxygen only lacks 2 electrons to be basically as powerful as a noble gas, because that's what that last column is on the periodic table. So what that tells you, because oxygen is not only to the right of hydrogen, but also lower than hydrogen, that tells you that oxygen loves its outer two electrons more than two hydrogens love their each outer one electron that fills itself up. Because hydrogen only takes one more electron to fill it up, and then the other hydrogen takes one more electron to fill it up. That's all fine, but that only promotes it to behaving at least as a noble gas like helium. Okay. But helium doesn't hold on to its two electrons nearly as good as the next element down in the periodic table. So that's the point. Now, because of that, that means the oxygen tends to win the battle of the holding on the electrons. So down here, Mickey Mouse's chin becomes negatively charged, and up here, Mickey Mouse's spot between his head becomes positively charged. And because of this is actually a physical structure. You know, it's a quantum mechanical atom, and it has a quantum mechanical molecule, and it has an atom of oxygen and two atoms of hydrogen that are bound to one another in a very robust way, so they don't just readily break apart. So it really does behave like a dipole. It has exactly the same amount of charge negative at the chin as it does the positive amount of charge between the ears. So that is a physical electric dipole. So that's what you want to think about electric dipole. Electric dipole is given the symbol P, is the electric dipole. Okay. And basically, you can look at it like this. What we're going to do is we're going to put a negative charge, and then we're going to put a positive charge of the same magnitude. So this will be negative Q over here, and this will be positive Q over here. And we're going to say that this distance right here is, say, L. So the distance between the center of the charges is L. Obviously, that L has a physical meaning on the molecule of water. You'd say that this distance, you know, is almost or about the same as, let's say, maybe the diameter of the oxygen molecule, as if that means something. Okay. But the main thing is it is a physical parameter that we could do various experiments on and make some sense of what it behaves like. And we probably conclude that it might be 98% of the diameter of what we call diameter of oxygen. Okay. The main thing is it's a number we can do. So what we do for the electric dipole is we then imagine a vector that points from the negative particle to the positive particle. That vector shall be called L vector. Okay. And notice the fact that it points from the negative to the positive means that the vector points in the exact opposite direction as the electric field. The electric field created by the dipole would push positive charges to the left, not to the right. So that's sort of a self helping mechanism just to help you remember the formula. So now that we have that, we can say the electric dipole is in fact Q times L vector. And that is a quantity we want to know. Okay, so that's something you got to commit to memory. I don't even know if you really have to commit it to memory. I think I did put it on our equation sheet, so it's fine. But that's the electric dipole. And as long as you've got something that tethers the two positive and negative charges together so that they act like one body, then it's behaving like a dipole. And in fact, if you subject this water molecule, for instance, to a rapidly changing magnetic field, what's going to happen is, or a rapidly changing electric field, either one really, what's going to happen is the oxygen molecule is going to flip back and forth, 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 as long as it's oscillating back and forth. So when that happens, there's actually a difference in energy of the oxygen being polarized this way versus that way. And that difference in energy is a very known amount of energy. So what happens is when it flips, it gives off a photon of a very specific amount of energy. And from quantum mechanics, we know that that energy is either h times the frequency or h times the speed of light divided by the wavelength of the radiation. So you can actually get the radiation of the particles coming out when those molecules flip back and forth. That's a whole nother part that you can get, for instance, in an MRI. In addition to the cool pictures that look like literally an anatomy classes chopped a person in half and allowed you to look down on the part that was cut in half. That's a cool thing about MRIs, but they also give you these curves that are basically like spectra. So it's like a plot of energy on the vertical axis versus wavelength or frequency, something like that on the horizontal axis. And it'll have a bunch of little spikes, and each one of those spikes corresponds to a very specific wavelength or frequency of energy. And because of that, we can look that up and say, oh, that spike corresponds to water, or this spike corresponds to a certain electron jumping to a certain orbital from another orbital, or something like that. But the main thing is, because of that, we can actually identify very specific atoms or molecules, elements or compounds in a body as well. So, for instance, that was one of the things that happened shortly after we started making some sense of Alzheimer's disease. Alzheimer's, which my grandmother was diagnosed as having in her 50s, like really, really young, like in her late 50s. And it was really a terrible thing for me. I spent a lot of time with my grandmother, but she was just losing track of everything. But they diagnosed her with pre-senile dementia. And later they told us that, well, technically that's going to be called Alzheimer's. And what they found shortly after that, because this would have been like the late 70s, early 80s, what they found shortly thereafter is that MRIs of patients with Alzheimer's disease were coming back showing that there was aluminum in their brain. And for a brief period there was literally news stories where people were thinking, well, maybe we should stop using aluminum pots and pans, and maybe we should stop using aluminum to can our drinks and stuff like that. Well, ultimately, it worked out that basically some part of our brain chemistry, biochemistry, uh, that little thing creates the metal and also partly causes Alzheimer's disease and other things. So it turns out that the aluminum's not a symptom of the Alzheimer's, it's almost a part of the cause. Okay. So it's, and I don't want to say cause, I haven't kept up with the research enough, but I do know that they've ruled it out as a cause. So anyways, that's one of the things that electric dipoles can do for you. But they have this really neat property because look, one's positive, one's negative. If you just had a positive charge, you know that the electric field falls off like 1 over the distance squared. So if I go a distance of 1 meter from the a charged positive Q, maybe I have an electric field of 100 newtons per coulomb. If I go instead of 1 meter away to 2 meters away, all of a sudden that electric field drops from 100 newtons per coulomb down to 25 newtons per coulomb. That's kind of a neat thing. But what do you think a positive and negative charge together do when you get a far distance away? Well, it turns out they fall off quicker than 1 over r squared. They fall off as 1 over r cubed. That's part of what we're going to do here. I'm not going to derive that part. Your book does it, but I'll definitely give it to you. So what I'm going to do now is I'm going to embed this electric dipole in a electric field. So what I'm going to do is I'm going to imagine right here, actually, I'm going to imagine right here a charge that's positive, and then I'm going to imagine over here a charge that's negative, and I'm going to imagine that that's my electric dipole, and now I'm going to immerse it in a electric field pointing to the right. So this is a large uniform electric field pointing to the right. And remember, electric fields point in the direction that a positive charge would be compelled to move. So instantly what we know is there's going to be a force on this positive charge pushing it that way. And there's also going to be a force on this negative charge pushing it this way. Now, that would tell you the net force on a dipole is 0, and in some sense, that's obviously right? But because those two charges are separated by a distance, they make sort of, you can think of it as making a couple. If you've had statics already, you know that what a couple is. We think of it as something having a torque, okay? So what I'm going to do is I'm going to imagine that the center of this is sort of the axis, and I'm imagining the torque that's acting on it. I'm going to say the total distance across here, of course, is L. So I'm now going to calculate the actual force or the actual torque on this dipole. So what we do know is torque is equal to R cross F, where R is the lever arm. It's the vector that points from the center of rotation to the point of application of the force. So in this top case, you would say this guy right here is the R for the positive. And you'd say that this guy right here is the R for the negative. Okay. So if we just look at this for a second, we see that the positive force tends to rotate this in a clockwise direction, but the negative force also tends to rotate it in a clockwise direction. So I can just work with the magnitudes and just add them. I don't have to work with the actual signs and all that. I don't have to work with the vectors. I can just work with the magnitudes because they're both causing a clockwise rotation. So I'm going to say the magnitude of the torque is going to be the lever arm, which I think you can see is L over 2, right? The length of it really is L over 2. And then the force is going to be, since the force is Q times E, remember F is equal to Q times the electric field. So I'm going to get the Q times E for the force for the positive charge. And then remember A cross B has a magnitude given by the magnitude of A times the magnitude of B times the sine of the angle between them. Well, the angle between them means if you put those two vectors tail to tail. So if I actually scoot my R vector up here, you can see they're tail to tail, and you'd see that this would be the angle theta. Well, that angle theta happens to be the same as the angle theta that the dipole makes with the electric field. Okay. And in fact, if you take F and multiply it times the sine of theta, you're going to get the component of F that's perpendicular to the lever arm. And that's exactly what we want, because only the component perpendicular to the lever arm can rotate it. Component parallel is just like pushing laterally on a hinge and hoping the door is going to open. It's not going to work, right? So this one's going to be QE sine theta, and then the other one's going to be L over 2 times QE. And lo and behold, we're going to get the same sort of scenario where this is the angle theta. So we're going to get QE sine theta again. So this actually adds to become L over 2. Excuse me. We can get rid of the L over 2 now. We can just say L times Q times E sine theta. And lo and behold, what that means is, since this quantity right here is the magnitude of the dielectric, electric dipole moment, I mean, not dielectric, it's the magnitude of the electric dipole, then we now know that torque can be given by torque is equal to P cross E. So that's an important formula that we use day in and day out in electrical engineering, physics, and electricity and magnetism in general. Not only that, it's one of the first things where we start to see exactly how similar electric and magnetic fields are, because there exists a magnetic dipole as well. That magnetic dipole is given the symbol mu, and then lo and behold, the torque on a magnetic dipole is actually mu cross not the E, but the B, where B is the magnetic field. So you can see already how the magnetic field and the the electric dipole and the magnetic dipole, and therefore the magnetic field and the electric field, are on the same footing and very similar. Any questions on that one? So just know this, we do expect you to know how to do cross products and dot products and that sort of thing. So if you need any help with that, there's a ton of those videos on my YouTube channel. You can check that out. The other part of this that we need to get is that work, we learned in circular motion that work is equal to F dot DL. We actually learned that in the 241 class. But once we got to the circular motion, we discovered that that could also be written as T times, or tau times d theta. It turns out when you carry that process out, you know that the work can equal the potential energy. That's exactly the way we did it. Remember, we calculated the work in lifting an object of mass m in a gravitational field, lowercase g, and we lifted a distance h very, very slowly so that we could just barely put enough force, which would be mg, on it. And then mg times h became the work, but mg times h also was the potential energy. So in this case, we're going to find out, and your book will do this derivation for you. So I'm skipping the time because we don't have enough time now. I'm just going to give it to you. But U is actually equal to negative P dot E. That's the formula for the potential energy of a dipole. And guess what? Sure enough, U is also equal to negative mu dot B. And that's what you get on the magnetic side. So again, we get another similarity. The last thing I wanted to show you was that basically the electric field some distance away from a dipole is actually exactly the equivalent of P over 4 pi epsilon naught r cubed, where P, remember, is Q times L. Okay, so this is only true for R much, much greater than L. Or I should leave off that vector symbol. So that's the other thing I wanted to let you know. So that's the last of chapter 21. Anyone have any questions on that stuff? All right. Well, the next chapter, like I said, we normally can do that in a single day. What I'm going to do is get you started by getting you thinking about a concept called electric flux. So we're going into chapter 21 or 22. And we're going to be talking about Gauss's law. Okay. But we're also going to talk about electric flux. Okay. Electric flux is given the symbol uppercase Greek phi or phi. I think that's pronounced phi. So what I want you to imagine for this is, let's imagine a hole in a floor. So we're imagining a super modern house or office building or something like that that has a very, very thin floor. I mean, it's held up, it's structural and all that good stuff, but it's just not that thick compared to how high the ceiling is. So we're looking at a floor like on a second story or something like that. And then down below it is a floor where a Mack truck or actually a dump truck can pull under it. So let's think about that for a second. What I'm going to do is say, let's imagine there is a hole in the floor, in the ground, or in the second floor, if you will, like this. So that's a hole in the floor, and I'm going to mean the floor is very thin, and I'm going to show that by putting this here. So the floor is kind of thin, as you can see from these dotted lines right here. But directly down below it is a dump truck whose bed is exactly the same size as this hole. Okay. So what I'm now going to do is put a dump truck bed right here. And here's the roof of the dump truck. And here's the window of the dump truck, the windshield, and the hood, something like that. And then the tires right here. Obviously, we don't need this much drawing, but the main thing is I wanted you to get some kind of picture of it, something like this. And what we're trying to do is we're trying to clean stuff off the second floor by throwing objects down that hole that should land directly in the back of the dump truck. But since the dump truck is exactly the width as the hole, there's a problem because one, the dump truck and the hole are the same size, and two, the distance from the hole way up there down to the dump truck way down here is pretty huge. So if the trash that you throw has any velocity horizontally, it's going to completely miss the Mack truck. So if it has velocity that points into the page like this or out of the page like that, it's probably going to miss the Mack truck, or excuse me, the dump truck. Or if it has a component of velocity this way or this way, it's probably going to miss the dump truck. Okay. So what you might want to do is take or try to figure out some way to calculate what velocity vectors are able to go through that hole. So what we could do is we could imagine this hole defines a area like this, and we could in fact define that area as a vector. And there's a lot of different vectors we could use for it. For instance, we could take a vector going horizontally or just slightly not horizontally, slightly like that. All these different vectors could be good representatives of that area. And there's no real good reason to take one over the other. So the thought is maybe we should take it perpendicular to the area of the hole. And by doing that, then there's only two choices of what it could be. It could be either perpendicular down or perpendicular up. Well, it turns out we can't really make our mind on that for just a hole. But if we start talking about a closed surface later, we can use something to define what it's going to be. So at the end of the day, we're going to define the area of the hole by a vector called A. So what I'm going to do now is I'm going to say there's a vector A. And let's say this side is 3.00 meters and this side is 2.00 meters. So this vector A, you can see by these drawings, is perpendicular to the surface, but also the vector A has a magnitude of 6.00 meters squared. Now, we could also do it this way. I could do, for instance, this way. And area would be equal to 6.00 square meters, and it'd still be perpendicular, and that's perfectly acceptable as well. In fact, that one might be a little better. So what we might want to do to ascertain whether a certain velocity that we're throwing trash with is going to make it through is we want to find the velocity vectors that are actually perfectly parallel to A. And the test for parallel to A is that the dot product is not zero. If the dot product is zero, it's perpendicular. So we can think about the particles that actually go in by V dot A not equal to zero implies might make it. Okay. In fact, if we did V dot A and found they're exactly perpendicular, then every one of those are going to make it. But the farther and farther off you get from being perfectly parallel, the worse and worse you get at having a chance of going in. So that's actually what flux is. You can think of flux as the electric field dotted with a differential area vector. So in the same way, we're going to make the electric flux, but we're going to allow the surface to not be some smooth thing like this window. It could actually be the surface of a sphere. So we'd have to hack it up into itty bitty squares and then take the area vector for that And if we find the electric field varies by too much over that square, we're going to have to dice it up smaller. So you keep going smaller and smaller and smaller until you can get one electric field vector to represent that particular area. Then you take the dot product of it, and then you add that to the next one for the next little cube. So lo and behold, we get the integral of dA is equal to the electric flux. So we will work with that next time. It's now 6:41. That should give you a little bit to think about. And we'll start with this next time. I'll go ahead and derive Gauss's law in some sense, and then we'll use it. And that should be, we'll literally finish chapter 22 that same day. Because the way chapter 22 works is there's pretty much 3 different types of symmetries that you can use Gauss's law for. And we're going to spend the next several chapters reusing those Gauss's law calculations over and over again. So you get plenty of practice that way. So you guys are free to go. Don't forget to chat me your first and last name so I know you made it here for the roll. And I will see you all next week. Remember, our test is going to be Wednesday, or excuse me, it's going to be Thursday excuse me. You guys are doing it via proctor at one of the testing centers. You have up until literally Monday of next week. Sunday's what we're shooting for, but in principle, we could do Monday. So have a good one. Berenice, are you still here? Yeah, there she is. Anybody else
Yes,
have
sir.
any
I'm still
questions?
here.
Yeah, I see you, Berenice. How can I help you?
I just had a couple questions for
Mhm.
concepts that are going to be on the test for tomorrow.
Okay. Anything you want to share your screen with me for, or?
Yes, sir. I have like 3 different tabs open right now with problems. So let me cut to the right one. How have you been doing, Professor Younger?
Not too bad. Got to come home a little earlier today than normal, and things are nice. Got some work done. Stuff's good. How about you?
Doing good. I got one of my midterms finished. So
All right.
that's like one more sigh of relief there. All right, I think I found it. I think this is the one. Which one am I sharing? Yes, this one.
By the way, what button are you pushing to make it share? Because I sometimes have students ask me that.
I am pushing, I'm on the Chrome tab.
Okay.
I'll click share screen and then I did the Chrome tab.
Okay, gotcha. I was just
For
curious.
sure.
I don't see what it is from your perspective, so I want to make sure I could answer that in the future.
Yeah,
So,
I prefer that one because the share entire screen can be a little,
yeah, that shows you everything your desktop, which probably has a picture of your dog or your cat or something.
oh, um, let's see. I don't know how much time you have. I don't want to take away any of it, but this is one of the problems from looks like the second online test we had.
Okay.
So
I'm
I
not
got,
seeing it yet. It came up for a second and then popped back down. So I'm thinking
oh
something
no.
happened.
Okay, let me try resharing again. I might try the window this time. Try it again.
I got it.
Okay, sweet. So yeah, this is for the second online test we had over chapters 3 and 4.
Mm-hmm.
So like the chapter 3 concepts I got wrong had to do with vectors, and I've like gone back and looked at those. So I think I've, can figure those out now. But yeah,
This
some of
one's a
these
really good problem. It's one I like to give on the test, but one I forgot to solve for you guys in class, so I didn't give it to you on the test. But I'm glad you asked about it. Have you drawn your free body diagram for this yet?
I have not. I can try to find my old notes. Let's
Well,
see.
what you want to do with this is you're going to draw a vertical axis that be like your y-axis. The x-axis isn't even needed here, but you can go ahead and draw it just to keep it from looking weird. And what you're
Okay.
going to do is just put a little dot at the origin, and that's going to represent your 60-kilogram person.
Okay.
Okay. The forces acting on them, remember the rule I told you guys is you look at everything that's touching the object. So the 60-kilogram person, you're picturing them riding on an elevator standing on a scale. So evidently the only thing touching the person is the air, but we're ignoring any kind of air resistance or that kind of stuff. So we don't worry about that one, and the scale. So not only that, I think you would agree that the scale is probably pushing upward on the person. Would that make sense to you?
Yeah, because if the person is pushing down the scale with the 60 kilograms, then the scale would be pushing up on it, right? Like the
Yeah,
same,
not necessarily the 60 kilograms, but yeah,
like
their
the
weight
force.
is going to be affecting it. Yes.
Okay. Yeah. All right.
Okay. So you got the
Uh-huh.
60 kilogram dot, and then you got a F sub S. That would normally be in class. I would have called that F normal, but in this case, I'm going to call it F sub S because it's a scale that's doing the normal force work. And in fact, it's the force that the scale puts out that it reads as the object's weight. So Fs pointing up is the force on it. Now, that's the only thing touching it. So I also said once you've run out of all the things touching it, then you look for the things that can apply forces without touching it, i.e., the action at a distance stuff, which is gravity in this case. So, do you know what the force that gravity puts on something's called? Starts with a W.
Be weight.
Yeah.
So M times G.
Yeah, exactly. So M times G, that points downward.
Okay.
Okay.
Through.
Now, obviously, the answer choices are saying upward and downward with acceleration. So, what you're going to have to do is you're going to have to assume the acceleration, for instance, is in the upward direction. Now we draw free body diagrams. We don't draw acceleration diagrams like some statics classes and stuff like that. So we just draw a free body diagram, but off to the right, say you can draw an acceleration vector up, not attached to anything, but just to remind you that in F equals ma, here's A, it's going to go up. We can also treat that as if it's pointing down just by replacing it with negative A. So that actually handles both. Now all you do is you write the summation of the forces in the y direction is equal to mass times acceleration. What do you get when you do that?
Okay, just to make sure I'm tracking.
Mhm.
Um, so back to the part about like the direction, right, with acceleration. So
Right.
you're saying with these specific problems that acceleration is positive?
It could be up, and that's the direction I called positive, in which case the
Mm-hmm.
acceleration would be positive, but it might turn out to be downward. We've got to figure that out because they've given us what the scale reads, which is 400
Mm-hmm.
newtons.
Mm-hmm.
And we've got to figure out a way, either with accelerating up or accelerating down, which way that gives us a F scale equals 400 newtons. Because remember, 60 times 9.8 is not 400. 60 times 9.8 is like 570, 580 or something like that. Oops, I hit the wrong key. Yeah, it's 588. So this is a markedly lower weight than you really expect. Have you ever tried jumping on an elevator?
Uh, I think other people have with me in it. It
Yeah,
like
so I do
shakes.
that. I do that all the time, especially with my kids. But the neat thing is when you're accelerating upward, you if you try to jump, you feel like your legs are really getting a workout because it's actually harder to jump when you're accelerating upward. If you're
Uh-huh.
just coasting, from second floor up to the 80th floor, that's more or less going on at constant velocity. So you can jump all you want, no problems. But then the neat thing, and this is what I used to do with my girls, is as we were starting to come to a stop at the appropriate floor, that's an acceleration downward. And what I would notice is I'd feel really light. And in fact, I could jump and my head could touch the ceiling, which normally my head can't because I'm not that tall, right? So I know for a fact that when something's accelerating in the downward direction, that my weight becomes smaller.
Hmm.
So I would use that, and then instead of saying the acceleration is going up, since this number is smaller than 588, I would maybe try the arrow off to the right pointing down and call that A. But Now that you have the free body diagram, you can go ahead and write Newton's second law, which says the summation of all the forces is equal to mass times acceleration. So what would the left-hand side of that equation be?
So I'm going to be adding the weight from the scale, or the force.
Yeah, the force scale, F sub S, right?
And it'd be F sub G, so like the weight.
Okay, that one would be the mg, right? Now, would it be Fs plus mg, or would it be Fs minus mg, or mg minus Fs, or what?
Hmm.
Did you draw a positive y anywhere to tell you which way is the positive direction? You can make it up or down.
Yeah. Oh, okay. So because we were saying that F sub S is equal to the normal force,
Is like the normal force. Yeah, it's the force scale's providing, right?
which is pointing upwards. So then that would be in the opposite direction of the weight.
Exactly. So one of those is going to be positive and the other one's going to be negative, and that all depends on which direction you call the positive direction. You're going to call, I just told you the acceleration going down is our more likely answer. So maybe it might be smart to put the positive y-axis pointing down.
Okay. So then I'll do F sub G minus the F sub S.
Yes. Yes. The F sub G, which would be mg. So you're going to do mg minus F sub S. That's exactly right. And that's equal to
That mass times.
times the A. And since you chose down as positive and you're hypothesizing that the acceleration is down, then you just call it m times positive A as opposed to negative ma. Okay. So now what you want to do is substitute for the Fs, put in 400 newtons there.
Okay.
And for the mg, put in 588. And for the m, put in 60. And see if you can solve for A.
All right. Oh, solve for A. That's right. Right. I get, let me double check that again. Divided by 60. 3.13 repeating.
3.13 repeating?
Mm-hmm.
Yep, that sounds about right. So you got that and you said downward. So I'm thinking it's probably the 3.14 roughly.
Yeah, 3.14 downward.
And that's basically it. Now, it's normally not asked this way. This is actually a much more complicated version. Normally, I'll ask you what's the apparent weight when the object is accelerating upward at such and such acceleration. Or I'll ask you what's the apparent weight when the object is accelerating downward at, some acceleration. This one's actually harder where they're actually trying to get you to use your understanding of acceleration to find the acceleration given the two weights, or given one of the weights and being able to calculate the other. Does that help you? Do you think you understand that now?
I understand the concept a little more. I'm still, I guess, trying to wrap my head around the acceleration part and like it being in the direction of the elevator, and like how we knew that acceleration was in that direction.
Yeah, so there's two ways this could happen. Acceleration downward could be you going from 0 to some velocity greater than 0, but in the downward direction. That would be an acceleration downward. And that would be more like what you've seen on cartoons where, for instance, Wile E. Coyote runs off the edge of a cliff and then all of a sudden realizes he's in the air and falls down. So it's sort of that delay between gravity acting and not acting. that's sort of what you can think of with the elevator floor. It's just sitting there. And if you imagine yourself like Wile E. Coyote, when the elevator took off, you would be left there and you'd be a little less heavy, right? Because
Mhm.
you're obviously not heavy enough to keep a touch to the ground. So that's one way of thinking about it. So if the elevator left from out from under you, that would make your weight seem a little less. Now, the other thing is you could also be going really fast upward and then all of a sudden start to slow down or literally go from a high velocity upward to a zero velocity. And that would, in some sense, you pictured of it slinging you up. That's the same thing. You're again experiencing a lower weight. So both of those scenarios are accelerations downward. So when the
Oh,
elevator first took off down, you'd feel
mhm.
light, or when the elevator is coming to a stop up, you'll feel light. Also, when the elevator is taking off up, you feel heavy. And when the elevator is I'm trying to think of the other way it would make you feel heavy. Up, taking off heavy. And yeah, I can't think of the other way right now. But anyways, you know the two ways that you can make it feel light. That help?
Yeah, that does help. I'll kind of try to do
It's
some
sort of
practice.
like the problem we worked the other day where I did it the scale on the equator and then I did the scale at the North Pole. It's the same sort of problem, only the acceleration there was necessary to keep you going in a circle around the equator of the Earth, whereas here it's just an acceleration due to an elevator.
Okay.
Okay. I got time for maybe one more question.
Okay. Let me see if I can find. Let me see what else I have open here. I did that one. What is this? Oh, shoot, I don't know. This is something I'm working on right now. I think that's the only like problem I had a question about. These were more conceptual.
Okay. You can send me pictures via texting. I know you have to take your
Mhm.
test tomorrow. I don't know if you're taking it in the morning or afternoon, but you can send me text messages, and if I have time, I will reply to them. I know you've got a short turnaround because you're taking the test tomorrow, so I'll do my best to reply to you. I do have a couple students in the queue already. I know somebody texted me about some question and asked me if they chose the wrong answer and some other stuff. That wasn't you, by the way, was it?
No, that was not me. Yeah, I didn't send
Gotcha.
a message. Hmm.
But yeah, you're
But yeah,
welcome.
I'll go on and jump off here and Professor Younger, but I appreciate it, and
You're welcome.
I may send you a message. I'm gonna try
Okay.
to
And don't
homework.
worry, I mean, if you send it late, it's not a big deal because I turned my phone off where it doesn't wake me up. So if you send it too late, I'll get it in the morning and you won't wake me up or anything. That's why I keep telling students it's okay if they send it. My wife would beat me if it actually aggravated me, but I got to sit up where it won't. I'm not saying my wife would beat me, by the way. I'm just being funny.
Uh, can't have
Right, right,
that.
right.
You have a good evening. Thank
All right.
you.
You too, Bernice. Have a good day. Bernice, sorry.
Oh, no, you're fine. Bye.